last class we started out investigating the Schrodinger equation for a particle in three-dimensional potential, and we restricted ourselves to a potential which was spherical symmetric. And we saw that this led us to investigating the properties of the angular momentum operator, and that is what we have been investigating in the last class, the latter half of the last class. And let us continue with that in this class. So, in classical mechanics, the angular momentum, the three components of angular momentum, Lx, Ly, Lz, are written over here. So, you can easily work these out from the definition that the angular momentum L is equal to r cross p. So, Lx is ypz minus zpy, etc. We used the operators for y, for these various x, y, z, the various coordinates, and the corresponding momenta to write down the operators for the angular momentum. So in quantum mechanics, angular momentum, we saw yesterday that angular momentum is represented by these three operators. Lx, Ly, and Lz are represented by these three operators, and we wanted to work out the commutation relation amongst these three operators. We also saw that the commutation relation amongst these three operators could be expressed as follows, that Li, the commutator of Li with Lj, was equal to I h cross epsilon I j k L e, where I, j and k are indices which run over the value 1, 2 and 3. So let us look at another example of this. Let us put I equal to 3, j equal to 2, and work out what this commutator will give us, just as an example of this notation. So, if I is equal to 2, then what we have is L2, the commutator of L2 with L3 is equal to I h cross epsilon 2, 3, I and k are respectively, and we have k here, L k. I also told you that if any index is repeated, it has to be summed over all possible values. So k will take all possible values, which means it will go over 1, 2 and 3. When k is 1, we have epsilon 2, 3, 1. Now how much is epsilon 2, 3, 1 is the question. So epsilon 2, 3, 1 can be obtained by a cyclic permutation of epsilon 1, 2, 3. So we have epsilon 1, 2, 3, and if we do a cyclic permutation, that is, we shift the 1 from here to here, what we get is epsilon 2, 3, 1. If this particular combination 2, 3, 1, which we have over here, can be obtained by a cyclic permutation of 1, 2, 3, then it remains plus 1. This follows from the fact that epsilon ijk is antisymmetric with respect to the three indices. If it cannot be obtained by a cyclic permutation, then you have to actually interchange two of them once, and that will give a minus sign. Okay. So epsilon 2, 3, 1 is equal to plus 1. So this is equal to I h cross epsilon 2, 3, 1, which is plus 1 into L3. L1, sorry, 2, 3, 1, L1. K will also take the value 2. When k takes the value 2, this epsilon is 0, and when it takes the value 3 again, epsilon is 0. So this basically implies in the usual notation that L y Lz is equal to I h cross Lx. Okay. So this is what the notation means. So we just considered another example of this commutation relation. Now let us move ahead. Another commutator which we want to calculate is the commutator between L squared. So we also want to calculate the commutator of any component L, let us say Li with L squared. This is another important commutator which we want to calculate. How much is this? So, let us calculate it for a particular value of I. Let us calculate it for Lx, for example. So, we want to calculate it for I equal to 1, or we have Lx. L squared is the sum of is Lx squared plus Ly squared plus Lz squared. Because L is a vector, I have to take a dot product, which gives me Lx squared plus Ly squared plus Lz squared. Now, we know that Lx commutes with itself. So, the first two terms, this commutative with this, gives us 0, and what we have left is Lx with Ly squared plus Lx with Lz squared. Let us evaluate these two commutators one by one. So, let me evaluate the first one. So, let me first evaluate. So, the first commutator over here, it gives me Lx Ly squared. This is the first term, and I have a minus, let me write it here, minus Ly square Lx. So, this is the first commutator. I am going to put in two more terms which will help me evaluate this commutator. So, I am putting in two more terms which exactly cancel out. Now, I can write this, the first two terms, I can take Ly common on the right hand side, and the first two terms become the commutator of Lx with Ly and the second two terms, they become the commutator of, I can take Ly common on the left hand side now, and we know that the commutator of Lx and Ly is I h cross Lz. So, this is equal to I h cross, and then I have Lz Ly plus Ly Lz. So, this is the first term. We have another term. Let us evaluate the second term. So, this is the second term we are going to evaluate here. So, the second term can be written in a similar way. So, the second term is the commutator of Lx with Lz. So, I have Lx Lz squared, and I write the minus Lz square Lx over here. Now, we repeat the same procedure. So, we put in an extra Lz Lx Lz over here, and we add the same term. Now, the first two terms can again be grouped into one commutator, which gives us we can take the Lz common on the right hand side. So, what we have is Lx commutator with Lz, and we have Lz over here, and we have plus the commutator of, we can take Lz common here, Lx comma Lz and what this gives us is equal to now what is the commutator of Lx and Lz? Let us look at that. So let us calculate that here. So Lx Lz is L1 comma L3 is equal to I h cross epsilon 1 3. We know that the only other term, only non-zero term will be 2. So we have L 2 over here. Now we have to determine how much is epsilon 132. Now epsilon 132 is equal to minus epsilon 1 2 3, because it is antisymmetric with respect to interchange of any two neighboring indices. So if I interchange 3 and 2, I get epsilon 1 2 3 with a minus sign, and this we know is equal to 1. Epsilon 1 2 3 is 1, so this is equal to minus 1. So we find that Lx Lz is equal to minus I h cross epsilon into Ly. Okay. So we plug this back into the expression which we wanted to evaluate. We had encountered this commutator Lx Lz, and that turned out to be minus I h cross Ly. So let us plug this back into the relation we want to evaluate, and this gives us, so we have minus I h cross outside, which is common, and then I have Ly Lz plus Lz Ly, which we see is exactly the minus of the previous term. So this and this are negative of each other, and they exactly cancel out. So what we find in conclusion is that the commutator of Lx with L squared is equal to 0. Okay. So the x component of the angular momentum commutes with the square of the angular momentum, the operator corresponding to the square of the angular momentum. Similarly, the y component and the z component, if you work them out, I leave this to you as an exercise to work out the commutation relation explicitly, and if you work out the commutation relation, you will find that all of them commute with L squared. So we have obtained a set of relations which are extremely important in the study of angular momentum in quantum mechanics. These relations are the commutation relation between the angular momentum operators. The three components of the angular momentum operator do not commute amongst themselves, and we know what the commutation relation is. All the three components of the angular momentum operator commute with L squared. So L squared commutes with everything. Okay. Now let us go ahead further. We started out, so these are the properties of the angular momentum operator, and we shall come back to it. Now let us relate all of this to the problem we started out studying. We started out studying the motion of a particle in a three-dimensional potential which is spherically symmetric. And for studying a spherically symmetric problem, the spherical polar coordinate system is most convenient. So let us now express all of these things in operators in a spherical polar coordinate system, and let us work out what the operator L square is in a spherical polar coordinate system. Okay. This involves a little bit of pretty messy algebra, but let me at least outline to you the key steps, and then a part of it I can leave to you as an exercise to work out. Okay. But this you have to work out only once in your whole lifetime, and afterwards you can just use the results from the book. So I recommend that you work this out thoroughly at least once, and preferably now, so that you do not have to do it later on in your life. Okay. So let us let us work out these various components of the angular momentum operator in a spherical polar coordinate system. A spherical polar coordinate system, although it appears messy to you right now, has its own conveniences. So let us go ahead and do it. So let me first draw the spherical polar coordinate system again. This is x, y, z, and the vector r over here, which you would represent in the Cartesian coordinate system in terms of x, y, z, is now represented in terms of the distance r, the angle it makes with the z axis theta, and the angle, the projection into the xy plane makes with the x axis, which is phi. So the new coordinates are r, theta, and phi. So let me first write down the relation between x, y, z and r, theta, and phi. So z we know is equal to r cos theta x is equal to r. So the sine we have to project it here, which is sine theta, and then project it onto the x axis, which is cos phi. So this is equal to r sine theta cos phi, and y is equal to r sine theta sine phi. Let us also write down the inverse relations, which are, so r, the inverse relations can also be written down. So we have r is equal to square root of x square plus y square plus z square, and sine theta, rather cos theta, okay, cos theta is equal to z by r, cos theta is equal to z by r, and tan phi is equal to y by x. Now we want to represent the angular momentum operators in terms of these coordinates. So the angular momentum operators, let me first show you the angular momentum operators. So these were the angular momentum operators Lx, Ly, Lz. So in addition to x, y and z, they also involve derivatives with respect to x, y and z, and these derivatives have to be converted into derivatives with respect to r, theta and phi. So let us first work that out. How are the derivatives with respect to x, y and z related to the derivatives in terms of r, theta and phi? So we can express the whole thing in terms of a column matrix. So let me do that. So we can write the whole relation as follows: del del x, del del y and del del z. This is equal to a big 3 by 3 matrix over here into del del r, del del theta, del del phi. Let me first explicitly write down the terms over here, and then we can work out what those terms are. So the term which appears here, del del x, is equal to del r del x into del del r plus del theta del x into del del theta plus del phi del x into del del phi. Similarly, here we have del r del y, and here we have del r del z, and here we have del theta del y, and here we have del theta del z, and here we have del phi del y and del phi del z. So, we have to now work out each of these derivatives and put it into this expression, and then we have the relation between del by del x, del by del y, del by del z in terms of the derivatives with respect to r theta and phi. Let us do it, it does not take us much time to do this. So, let us work out each of these one by one. Okay. So, the first thing which we have to work out is del r del x. So, del r del x, this is equal to, so if you just differentiate the relation relating r with x square and y square and z square, if you differentiate this with respect to x, then you will get the same thing in the denominator, you will get a half, and then you have to differentiate x square, which will give you a 2, that will cancel away the half, and I will have x in the numerator. So, this is equal to x by r, which is equal to, x by r is just equal to sin theta into cos phi, sin theta cos phi. Okay. Similarly, del by del r del y is just sin theta sin phi, that is also very straightforward. Del r del y is equal to sin theta cos phi, because that will be y by r, and sorry, sin theta sin phi, thank you, and del r del z will be cos theta, right, cos theta. So, the first three derivatives have been worked out. The whole thing is just straightforward differentiation. So, let us, but it takes time to do it. Del theta del x. So, this to evaluate del theta del x, we can just differentiate this equation over here. So, if you differentiate this on the left hand side, you will get minus sin theta into del theta del x, and then we have to differentiate z by r. So, we have del theta del x into minus sin theta is equal to, if you differentiate z by r, what you will get is z by r cube, you will pick up a minus sign and you will have x over here. Okay. When you differentiate the r, you get 1 by r cube into x. Okay. So, this is equal to minus, now z we know is minus cos theta. So, this is okay, z is cos theta into r. So, one r goes away and x is sin theta cos phi, and only one r remains. So, del theta del x is equal to, so the sin theta over here and the sin theta over here, they cancel out, the minus sign cancels out with this. What we have left is cos theta cos phi by r, cos theta cos phi by r. Similarly, del theta del y is equal to cos theta sin phi by r. The only difference is that you will get a y here and y will give you a sin phi. So, we have these two terms. Now, we have to also evaluate del theta del z. So, del theta del z, let us also evaluate del theta del z. So, del theta del z. So, now del theta del z can again be obtained from this. All we have to do is just differentiate this with respect to z. Now, we will have one term when we differentiate the numerator and another term when we differentiate the denominator. So, so what we have is this into minus sin theta is equal to, if you differentiate the numerator, you will get 1 by r. If you differentiate the denominator, you will get minus z square by r cube, which is equal to z r, okay, it is equal to r square minus z square by r cube, and r square minus z square is just sine theta, because z we know is r cos theta. So, r square minus z square is sine square theta. So, this is equal to sine square theta by r. So, del theta del z is equal to minus sine theta by r. Okay. So, we have 3 more derivatives to evaluate. So, let us also do that. The next 3 which we have to evaluate are del phi del z. Del phi del z is 0. Let me show you the relation for phi. Tan phi is equal to y by x. So, if I differentiate this with respect to z, it does not change. So, del phi del z is equal to 0. Del phi del x. So, this can be easily obtained by just differentiating tan phi is equal to y by x. So, if I differentiate tan phi, what I get is sec square del phi del x into sec square phi is equal to minus y by x squared. Now, let us express this whole thing in terms of angles. So, what we have is del phi del x is equal to, if I take the 1 by cos squared phi into that side, then I will have a minus cos square phi, and y is equal to r sin theta sin phi, r sin theta sin phi, and in the denominator I have r squared sin square theta cos phi. So, let us see which of these terms cancel out. So, the r, one of the r's will cancel out with this r over here, cos square phi, there will be a cos square phi here, this will cancel out with this, and one of the sin thetas will cancel out with this. So, what I have left is sin phi by sin theta with a minus sign. So, del phi by del x is equal to minus sin phi by sin theta into r, sin phi by r sin theta. Let me also work out the last derivative which is required, which is del phi del y, del phi del y. So, del phi del y, again we have to differentiate this, tan phi is equal to y by x, and if I differentiate this, then what I get is again sec square theta. So, I get a sec square phi here, sorry, sec square phi is equal to, now just the y gets differentiated and this is equal to 1 by y, which tells us that del phi del y is equal to cos square phi, this gives you a cos square phi there, 1 by x, yes, divided by x, and x is equal to r sin theta cos phi. So, del phi del y is equal to, we have cos phi in the numerator divided by r sin theta. Okay. So, now let us put all of this back into the matrix relation, and then we can use this to calculate all of the components of Lx, Ly, Lz in spherical polar coordinate systems. So, let me put it back into the matrix relation which we have. So, the relation which we have is between del by del x, del by del y. So, the first thing here is del by del x, and then I have del by del y, and here I have del by del z. This is equal to, let me put all the terms here one by one, and finally over here let me keep some space. Here I have del by del r, del by del theta, and del by del phi. So, let me now put in the terms one by one. So, the first term which we have is del r del x, which is sin theta cos phi. So, here we have sin theta into cos phi, sin theta cos phi, and del r del y is sin theta sin phi, sin theta sin phi, and del r del z is cos theta. So, the first three terms are in place. Now, del theta del x is equal to cos theta sin phi by r. So, cos theta, no, del theta del x is cos theta sin phi by r. Cos theta sin phi by r. Del theta del x. Oh, right, del cos theta cos phi. Sorry, I was looking at the wrong one. It is cos theta. Thanks. Otherwise, cos theta cos phi by r, and this is cos theta sin phi by r, cos theta sin phi by r, and the third term is minus sin theta by r, minus sin theta by r. And the last three terms, we know that this one is 0, and del phi del x is minus sin phi by sin theta into r, minus sin phi by r sin theta, and the next one is cos phi by r sin theta, cos phi by r sin theta. Okay, so this is the relation between the Cartesian derivatives and the derivatives in the polar coordinate system. So, we do not require, so this is all that we need now to proceed. Let us use this to calculate Lz in the spherical polar coordinate system. So, we want to now calculate Lz. Okay. So, Lz is equal to minus I h cross x into del by del y minus y into del by del x. So, we want to calculate this in the polar coordinate system. So, let us proceed. Lz is equal to minus I h cross. Let us write down the first term. First term is x into del by del y. So, x we know is r sin theta cos phi, and del by del y, let us now work out how much is del by del y. Del by del y is sin theta sin phi into del by del r. That is the first term. So, let me write that down here, sin theta sin phi into del by del r, sine theta sine phi del by del r. Then we have the second term, which is cos theta sine phi by r into del by del theta. So, plus cos theta sine phi by r del by del theta, and then we have the third term, which is cos theta by r sine theta into del by del phi. So, let us also put in that, plus cos phi by r sine theta del by del by del phi. So, this is the first term, which is x into del by del y, and we have one more term, which is y into del by del x. So, minus y is r sine theta sine phi, this is y into del by del x. So, let me also put that here. Let us look at what is del by del x. So, the first term in del by del x is sine theta cos phi del by del r. Let me put that. So, we have sine theta cos phi del by del r. The second term is cos theta cos phi by r del by del theta. So, we have plus cos theta cos phi by r del by del theta, and then we have the third term, which is minus sine phi by r sine theta into del by del phi. So, we have the third term over here, minus sine phi by r sine theta del by del phi. So, we have got all the ingredients required to calculate Lz over here. Now, we have to just put this together. So, let us see what this gives us. Let us look at the first term, del by del r, the coefficients of del by del r. The coefficient of del by del r over here is sine theta cos phi into sine theta sine phi. If you look at the coefficient of del by del r over here, we find it is sine theta sine phi, sine theta cos phi, exactly the same thing, but with a minus sign. So, these two terms cancel out, this and this, they exactly cancel out. Similarly, if you look at the coefficient of del by del theta, you will find that the coefficient is sine theta sine theta cos phi, and we have cos theta sine phi. Similarly, here we have sine theta sine phi and cos theta cos phi. So, these two terms again exactly cancel out. And then finally, we have these two terms. Fortunately, they do not cancel out. Obviously, we know that this operator is not 0. It cannot suddenly disappear if you change your coordinate system. So, what we have left is this term over here, but del by del phi, and what this gives us is, let us write it down here. So, we have minus I h cross, and then we have r sine theta cos phi, sine theta over here and sine theta over here, r and r, they both cancel out. What we have left is cos square phi del by del phi, plus here we have minus minus, and then we have sine here and sine here. So, we have sine square phi this is a single derivative. So, finally, what we have is minus I h cross del by del phi. So, it is a bit of a relief that you do not have to deal with such a huge thing. At the end of the day, you are left with a simple expression. Okay. Similarly, you can use these to simplify Lx and Ly. I will not do that here. I will leave it to you as an exercise to work this out, to work out all three of them. Let me show you the final expressions for these. So, the final expressions I have got it here. So, these are the final expressions for the operators Lx, Ly and Lz in the spherical polar coordinate system. I have worked out the first one. I request you to work out these two as exercises, Ly and Lz, Lx and Ly. They are a little more complicated, but the procedure is exactly the same. Just that at the end everything lesser terms will cancel out, that is all. Okay. So, the next thing that we want to calculate using these is L squared. Okay. So, we want to use these three and square them and then add them up and use it to calculate L squared. So, now let us do that. That is again a little bit of algebra. So, today's lecture is largely devoted to algebra, but we shall draw some conclusions out of this shortly. So, let us now proceed to square each of them and add them up. So, we want to calculate Lx squared plus Ly squared plus Lz squared. So, this is again very straightforward. Let us do it. So, the first term is Lx Lz squared. Lz squared will have an overall minus sign from the I, and it will have a h cross square, and there will be del square by del phi squared. So, what I have is minus h cross square del square del phi square. This is the first term. Let me then calculate Lx squared. This also will have an overall minus sign and h cross squared. So, I can put that outside over here, minus h cross square is common, and then I have one term which is now if you look at this, okay, let us do it instead of trying to take shortcuts. So, the first term will be sine square phi into, so then I have plus, and I have to square this whole thing over here. You should remember that both of these are operators. So, when I square it, this operator here del by del theta can act on this cot theta. Similarly, the del by del phi over here can act on this sin phi. Okay. So, the first term over here is going to be sin square phi into and there will be one more term which is the square of the second. Let us see. So, there will be one more second term which is cos theta cos phi. Okay, let us write it down here. Let us work out each of these separately and then put it here. So, we are going to first work out Lz square is very simple. We will next work out what is Lx squared. So, let us work this out. So, this will have, we will work out the square of the content of this square brackets. So, that will have one term which is sin square phi del by del theta squared, and then we have a second term which is the square of this. So, the square of this is going to be as follows. It is going to be plus cot theta, then I have cos phi. I can take the cot square theta outside. I have cos phi del by del phi acting on cos phi del by del phi. This is the second, this is the square of the second term. The del by del phi over here can also act on the cos phi. The cot phi does not act on, so I can write cot squared, and then I have cos phi del by del phi, cos phi del by del phi, and then I have the cross terms. In the cross terms, we have to bear in mind that del by del phi can act on this sin phi, and del by del theta can act on this cot theta. So there will be two cross terms. The first cross term will be sin phi del by del theta, and then we have cot theta into cos phi can go outside anyway, let us keep it here now, cos phi del by del phi. So basically there will be two terms, one term when del by del theta acts on cot phi, another will be the second derivative, one with respect to theta and one with respect to a double derivative, one with respect to theta and one with respect to phi. And then we have another term which is plus cot theta cos phi del by del phi, the whole thing acting on sin phi del by del theta. So this is Lx squared, this is L x squared, this into is equal to this whole thing into minus h cross squared. Okay, let me not, this is equal to Lx squared divided by minus h cross squared. So let us simplify this a little bit more. So the first term remains as it is. The second term will have two parts now. One part will be minus sin phi. If it differentiates the cos phi, I will get a minus sin phi. So this the first term, okay, this is equal to sin square theta del square del theta square, the first term, plus there will be two terms, one when the phi differentiates cos phi, del by del phi acts on this, and another will be the second derivative with respect to phi. So let me write down the first one of the terms first, cot square theta cos square phi del by del square phi, and there will be one more term which is minus cot square theta sin phi cos phi sin phi cos phi into del by del phi. This is this term. Then we have another term over here. So here del by del theta can act on cot theta, and it can act on, it can come over here also. So let us write that. So we have one term which is sin, the cos phi can be taken outside. So we have sin phi cos phi del by del theta of cot theta, this is one thing over here, and then we have del by del phi. And we have one more term which is sin phi cos phi cot theta, and then we have del square del phi del theta. So this takes care of the third term over here, and then we have the fourth term, which again gives us two things. The first thing is obtained when I differentiate sine phi. If I differentiate sine phi, I will get another cos phi. So I have plus cot theta into cos square phi, cot theta into cos square phi into del by del theta. Okay, and we have one more term which is plus cos cot theta, and then we have cos phi sin phi del square del phi del theta. So today I will stop here. Tomorrow we shall also evaluate L y square, and then we will add up the two and then see what it gives us. Okay. In the last class, we were working out the various components of the angular momentum in a spherical polar coordinate system, and I had explicitly worked out what Lz was in a spherical polar coordinate system, and Lz turned out to be minus I h cross del by del phi, and I had asked you to also work out what Lx and Ly are in a spherical polar coordinate system. Then we had started out to calculate L squared, the operator L squared in the spherical polar coordinate system. So let us work out what the operator L square is in a spherical polar coordinate system today. So let me show you Lx, Ly, Lz again, Lx, Ly, Lz, and the operator L square is equal to Lx squared plus Ly squared plus Lz squared plus Lx squared plus Ly squared. So we have to square these three operators and add them up. We had set out to do this in the last class, so let us start afresh and finish it off today. So the first term, Lz squared, gives us each of these terms has a I h cross outside. Irrespective of whether there is a minus or plus sign, when I square it, I get minus h cross squared. So I can put a minus h cross square, overall minus h cross square outside. Then if I square Lz, then I get del by del phi squared. This is Lz squared. Now let me write down the various terms corresponding to Lx squared. So there will be one term which is the square of this operator. There will be one term which is the square of this operator, and there will be one term which is the product of this operator acting on this operator, and another term which is this operator acting on this operator. So let me write down these four operators over here. So the first term is sine square phi del del theta square. So we have sine square phi del by del square theta. The second term is the square of this operator. So the square of this operator, if you look at it, the del del phi, when I square this operator, del del phi will act on cos phi, but cot squared theta will remain unaffected. So I can put a cot squared theta outside plus cot square theta, and then I have cos phi del del phi acting on cos phi del del phi. This is the second term. Now we have the cross terms. So the cross terms, there are two cross terms. The first cross term will be when the product of these two operators. Del del theta will act only on cos theta. So I have one term which is sin phi cos phi, sin phi cos phi del del theta acting on cot theta del by del phi, and I have one more term which is this operator multiplied with this operator. Del del phi will act only on sin phi, so I have cot theta plus cot theta cos phi del del phi sin phi del del theta. So these are the four terms which arise from Lx squared. let me also calculate Ly squared. So Ly squared will have one term which is cos square phi del square del theta square. So let me put that down first. So I have a plus sign here, and I have cos square phi del by del square theta. Then I have the square of this term. Here again, del phi will act only on sin phi when I square this, rather will act on sin phi. So I have plus cot square theta sin phi del phi. Then I have sin phi del phi. Now I have the product of this with this, and del theta will act only on cot theta. So I have minus cos phi sin phi del theta cot theta del phi, and I have the last term which is this acting on this. So I have minus cot theta sin phi del by del phi cos phi del by del theta. So this is, let me put a square bracket here to avoid confusion. So this is the whole thing. And this can be now simplified. So let us see which of these terms cancel out and which of them remain at the end of the day. So del by del square phi doesn't cancel out with anything else here, and del by del square phi, let us see if there is any other term. Okay, let me just put down the terms, that will be simpler. So now let me put down the terms one by one over here. L square is equal to minus h cross square, and the first term passes through unscathed, del by del square phi. Now sin square phi del square del theta square, and here we have cos square phi del square del theta square. So we add up these two terms, we get just del by del square theta square. So we have plus del square del theta square. So let me mark the terms which have been taken care of. This is gone, and this is gone. Now let us see if any of these terms cancel out. So this term over here, sin phi cos phi del by del theta cot theta del by del phi, cancels out with this term which is exactly the negative of this. So this is also taken care of. Okay, so these two terms are gone. Let us see if any other term cancels out. So this has a cot squared theta, this also has a cot squared theta, but this has a cos phi, this has a sin phi. Now if we differentiate the cos phi, we get a minus sin phi. If we differentiate the sin phi, we get a cos phi. So if you differentiate this term, if del by del phi acts on cos phi and del by del phi acts on sin phi over here, these two terms, the resulting terms, are going to be just the negative of each other, and they will cancel out. So the only term which will not cancel out here will be when del by del phi goes through over here, and you will have del by del square phi. So what you have is cot square theta into cos square phi del by del square phi, and here you have cot square theta sin square phi del by del square phi. So these two terms contribute to give me plus cot square theta del by del square phi. Okay, because when this acts on the cos phi, it cancels out with the term which I get when this acts on sin phi. So these two terms are taken care of, and what remain are only these two terms over here. So let us see what the outcome of differentiating this is. So if I differentiate this, then I have, okay, if del by del phi acts on sine phi over here and del by del phi acts on cos phi over here, what does it give us? Let us see that. So when del by del phi acts on sine phi, it gives us cos phi. When del by del phi acts on cos phi, it gives us sine minus sine phi. So we have cot theta cos square phi, and here we have cot theta sine square phi. We get another plus sign, overall plus sign. So what we have is cot theta into del by del phi, because cos square phi and sine square phi give us 1. So the resultant of the sum of the two terms when del by del phi acts on sine phi and del by del acts on cos phi over here, the resultant of these two terms is plus cot theta del by del theta. There is one more term when del by del phi just goes through without acting on this, which will be a double derivative term, but that term will cancel out because I have cot theta cos phi sine phi and cot theta cos phi sine phi, but the signs are different, so that term will cancel out. So we have taken care of all the terms here, and the result is there in the is now this. So this is the operator L square in a spherical polar coordinate system. Let us simplify it further. So L squared is equal to minus h cross squared. Now del square phi, so the coefficient of del by del square phi is 1 plus cot square theta and these two terms can be combined and written as follows: 1 by sine theta del by del theta acting on sine theta del by del theta, because if we differentiate sine theta we get cos theta, which gives us the cot theta term, and we just have one derivative with respect to theta. And if I don't differentiate sine theta, but then I get del square by del theta square, and the sine theta cancels out. So this is finally equal to minus h cross squared. This is 1 by sine square theta. So I have 1 by sine square theta del by del square del theta square, del phi square, plus 1 by sine theta. Okay, let me write it. Now, so this is what we had set out to calculate, L square in a spherical polar coordinate system. Now let us go back to the problem we had started out with. We were looking at the Schrodinger equation for a particle in a three-dimensional potential, and this problem we had separated into two parts. One part was the radial part, and the other part was the angular part. We had used the separation of variables to separate this problem into two parts. So, the Laplacian operator del square, if we write it in a spherical polar coordinate system, it turns out to be this. Well, the radial part over here is wrong. It will be slightly different, but it does not make a difference as far as this discussion here is concerned. So, there is a radial part, some radial operator which acts on f. The expression given here is slightly wrong. I will rectify it when we come to it. Yeah, so we will do it. We will rectify it when we come to it. We don't require it right now. And there is the angular part, which only acts on the theta and phi dependence of the function. And the angular part we had written as some operator omega into f, where this 1 by sine theta del by del theta sine theta del by del theta plus 1 by sine square theta del square by del phi square was denoted by the operator omega. And using this operator omega, we had then been able to separate the equation into two different equations, the Schrodinger equation into two separate equations, one for the radial part and one for the angular part. And we found that the angular equation has to satisfy, the angular part has to satisfy this equation, omega acting on some function y of theta and phi is equal to some constant into y. Now, so this was how we had reduced the Schrodinger equation for a particle in a spherical polar coordinate, in a spherical potential into two separate problems, a radial part and a part which depends only on the angle. And the angular part had this operator omega. Now, here we have started from the angular momentum operators. If you convert the angular momentum to operators in quantum mechanics, and then if you calculate L squared, the square of the angular momentum operator, then we find that it comes out to be equal to, L square comes out to be equal to minus h cross square into the same operator omega, which appears in the problem of the Schrodinger equation for a particle in a spherical potential. Okay. So, this is the first point I would like you to note. So, the solving the Schrodinger equation for a particle in a spherical potential then reduces to solving this equation L square, omega is L square by minus h cross square. So, this is equal to minus L square y is equal to minus h cross square c y, right, because the operator omega is L square by minus h cross square. So, this equation, the angular part of the Schrodinger equation is the same as this equation over here, which basically tells us that these functions y are also eigenfunctions of the angular momentum operator, not the square of the angular momentum operator. Okay. So, this is the first point I would like you to note. So, the square of the angular momentum operator appears naturally in this problem of a particle in a spherical potential well. How does this square of the angular momentum, let us also look at the Schrodinger equation, the Schrodinger equation or the Hamiltonian. So, I have already also told you that the classical Hamiltonian can be written as the yes. So, I have already told you that the classical Hamiltonian in a spherical for any particle in a three-dimensional potential can be written as 1 by 2m the radial momentum squared plus the angular momentum squared by r squared plus the potential. This is the classical Hamiltonian. So, in quantum mechanics, the corresponding operator right? And the angular part of the Schrodinger equation comes about from this L squared. This, the operator corresponding to the radial momentum is just the radial derivatives, involves just the radial derivatives, and it is the angular momentum squared, L squared term, which gives us the derivatives with respect to the angular coordinates. And the separation of variables method separates these two parts into two sets of equations. Okay. So the angular dependence of the wave function for this is basically just the solution of the angular momentum problem. So we have to in order to study this problem, we have to basically look at the angular momentum problem. We have to look at the eigenfunctions of the angular momentum squared, the operator L squared, and those are the angular part of this wave function. Okay, so that is the reason that is the reason why we have started looking at the angular momentum operators. So this is the first point. The second point I would like you to note is as follows. We have worked out the commutation relation between the various components of L. We find that the different components of L do not commute amongst themselves. Right, this is not equal to 0. But all the components of L commute with L squared. Now, let us study an implication of this fact. Let us study two implications of this fact. The first implication is as follows. Let us look at the time evolution of the expectation value of the angular momentum. So suppose I have a wave function psi which describes the state of the particle, and psi will be evolving in time, and the time evolution can be calculated using the Schrodinger equation. Now the question I would like to address is, how does the expectation value of any component of the angular momentum, let us say Li, or any operator, any physical quantity, evolve in time? So we want to look at how this evolves in time. So we want to look at this. Okay. How does the expectation value of a particular component of the angular momentum evolve in time? So let us work out this quantity. So this is equal to d by dt, and here we have the integral psi x t, psi star x t, Li psi x t d cube x and this is equal to del by del t psi star. I am not showing the arguments explicitly anymore. So we have one term which is del by del t of psi star Li psi d cube x plus psi star Li del by del t of psi d cube x. Now del by del t of psi, we know what this is. We know that I h cross del by del t of psi is equal to the Hamiltonian operator acting on psi. If we take complex conjugate of this, then we know that I h cross del by del t of psi star is equal to h dagger of psi star, but h dagger is the same as h. So there should be a minus sign here. So we can use these two in this to calculate how the time derivative of the expectation value behaves. So let us do that. So what this gives us, del by del t of psi star, is that this is equal to I by h cross into I by h cross into the Hamiltonian acting on psi star. Okay, let us put it. Okay, this. Let us keep it like this, the Hamiltonian acting on psi star, and then I have Li acting on psi d cube x. Yeah, so this will be just a psi star over here. I am just taking complex conjugate of this equation, and then I have plus minus I by h cross psi star Li acting on h psi d cube x. Now, from the definition of Hermitian of the dagger operator of the conjugate, the dagger operator, this is equal to, I can take the I by h cross outside, psi star h Li dagger. There should be a dagger here, but the dagger of h is the same as h itself. So this is equal to this acting on psi d cube x with the minus sign here. No, sorry, the minus sign will appear here with the minus sign I by h cross, and here I have psi star Li h psi d cube x. So what do we get? We find that d by dt of the expectation value of Li is equal to I by h cross into the expectation value of the commutator of h with Li. This is nothing but the commutator, because I have HL minus LH. So this is nothing but the expectation value of the commutator. So we find that the expectation value of Li evolves, the rate of change of this is equal to I by h cross into the expectation value of the commutator of the Hamiltonian with the angular momentum. Now this is very similar to the equation of motion in classical mechanics. If you have done a sufficient amount of classical mechanics, in classical mechanics you will encounter exactly a very similar equation. The equation in classical mechanics for angular momentum, or for this equation holds for any observable quantity, not only angular momentum, for any observable quantity, its expectation value evolves exactly in the same way. The classical equation in for the angular momentum operator will be d by dt of not for the angular momentum, will be equal to the Poisson bracket. So in classical mechanics there is something called the Poisson bracket, which you might or might not have encountered, but the corresponding equation in classical mechanics is this. So the evolution in quantum mechanics is exactly analogous to the evolution in classical mechanics, except that you have to introduce the expectation values and I h cross, I and h cross. Okay, so let us not bother about this, since you might not have encountered the Poisson bracket till now, but let us work with this. So this tells us how the expectation value of the angular momentum operator evolves with time. Now for a spherically symmetric potential, the Hamiltonian is given by this. Now the angular momentum operator L commutes with the radial component of the momentum, because the angular momentum operator L involves only derivatives with respect to theta and phi. Right? We have just worked out what L is in a spherical coordinate system, and we see that the different components of L, Lx, Ly, Lz, all of them involve derivatives only with respect to theta and phi. Now in the Hamiltonian we have two terms. We have p radial squared, the radial momentum squared, and we have the angular momentum squared. The radial momentum involves only radial derivatives. So this obviously commutes with all components of the angular momentum. We have also seen that L squared commutes with all components of the angular momentum. So the commutator, and this also involves only the distance, so this also commutes with all components of the angular momentum. So the commutator h into the angular of h and the angular momentum is 0. So this is exactly equal to 0. So what this tells us is that d by dt of the expectation value of any component of the angular momentum is 0. In classical mechanics, we know that if a particle is moving in a spherically symmetric potential, its angular momentum is conserved. The analogous law over here is also the conservation of angular momentum. The quantity which gets conserved in quantum mechanics is the expectation value of the angular momentum. Okay, so this is the fact that angular momentum is conserved. So this is not only true for angular momentum. In classical mechanics, any quantity whose Poisson bracket with the Hamiltonian is 0 is conserved. Okay, or you may say that any conserved quantity in classical mechanics, the corresponding fact in quantum mechanics will be that the expectation value of that quantity is conserved. It remains constant as the particle evolves. Okay, not only for angular momentum, but for any quantity in classical mechanics which is conserved, you have the similar kind of fact in quantum mechanics. So this is one direct consequence of the commutation relation between these angular momentum operators and L squared. Now let us look at another consequence of this fact. The second consequence arises from the fact that the different components of angular momentum do not commute. All of them commute with L squared, and as a consequence, the expectation value is conserved in a spherically symmetric potential, but they don't commute amongst each other. Now, if we ask the question, can I have an eigenfunction, set of eigenfunctions, which are simultaneous eigenfunctions of Lx, Ly and Lz? The answer is no. You cannot have a set of eigenfunctions which are simultaneously eigenfunctions of all three components of the angular momentum. This arises from the basic fact that if two operators do not commute, let me write down the basic theorem. If two operators do not commute, it is not possible to have a set. By set I mean a complete set of eigenfunctions for which are set of functions, let me put functions, which are simultaneous eigen functions of both. Okay. So let us say that there is one operator A and there is another operator B. and the commutator such that AB is not equal to 0. The commutator of A and B is not equal to 0. Let us suppose that there exists a set of eigenfunctions, complete set of functions, which are simultaneous eigenfunctions of both A and B. Let us call it psi, let us label them like this: psi A1 B1, psi A2 B2, psi A3 B3. So these are a set of functions such that if A acts on psi A1 B1, it will give me A1, and if B acts on it, it will give me V1. Etc. For if it acts on A2 B2, then this will give me A2, and if B acts on psi A2 B2, it will give me B2. Okay. Let us suppose that there exists such a set of complete set of functions. Then any arbitrary wave function psi can be expanded in terms of these. If such a complete set exists, then any arbitrary wave function can be expanded in terms of this. So we can expand any arbitrary wave function as Ci psi ai comma bi, right? This just follows from the fact that they form if such a basis exists, a complete set of such wave functions, then you should be able to expand by the definition of completeness. Now let us work out what is the commutator of this acting on psi. Then this will be equal to, so the commutator is AB minus BA, and this will act on some Ci into AI comma Bi. Now when B acts on this, it will give me a number Bi, the state remains unchanged, the wave function remains unchanged, and then when A acts on it, it will give me Ai. So this will be equal to AI Bi minus Bi Ai and it will be equal to 0. So for any wave function, if the commutator of A and B acts on it, it gives 0. But I have already assumed that the A and B don't commute. But if the commutator acting on any wave function is 0, then we have an inconsistency. A and B don't commute, but the action of the commutator A and B on any wave function is 0. There is an inconsistency, which tells us basically that this is not possible. You cannot have such a complete set of eigenfunctions. You may have 1 or 2 or 3, whatever, a finite number of such eigenfunctions, which are such functions which are simultaneously eigenfunctions of A and B, but they cannot be a complete set of eigenfunctions, because if they were a complete set, then you could expand any wave function in terms of these, and then the commutator would have to be 0. Okay, so we have just proved that you cannot have simultaneous a set of eigenfunctions for two operators which don't commute. So what this implies is that you cannot have simultaneous eigenfunctions of, so it is not possible to have simultaneous eigenfunctions of Lx, Ly, Lz. So one eigenfunction, a set of eigenfunctions can either be eigenfunctions of Lx or Ly or Lz. Okay. So we have to choose one of them and work with it. So let us choose Lz. Okay, so we are going to work with eigenfunctions of Lz, the operator Lz, and the direction z can be chosen arbitrarily. It is up to us to choose which is the z direction, because the problem is spherically symmetric. So we can choose some arbitrary direction to be the z direction, and we shall work with the eigenfunctions of the component of the angular momentum in that particular direction. So let us, so we are going to work out eigenfunctions of this, and these eigenfunctions, let us say that we have some constant C1 is equal to C1 into psi C1. Okay, C1. Or no, C1 we have, okay, doesn't matter. C1 into, or better to use K, because C1 has been used in the expansion. Okay, so we are going to solve this equation. Now, okay, because the C's have been used as expansion coefficients for the wave function. So these psi k's are defined to be eigenfunctions of Lz. L squared commutes with all three of them. So this psi k will also be an eigenfunction of L squared. So this will be also an eigenfunction of L squared, and it will give us some number. So this number could be, let us say, C. Okay, I can have simultaneous eigenfunctions of L, and it should be C by minus C by H cross square for consistency. Okay, so these wave functions psi, or they have been actually denoted by y earlier, so we can switch over to y. So we want to work out a set of eigenfunctions which are simultaneous eigenfunctions of Lz as well as L squared, and they will not be, the whole set of eigenfunctions will not be also eigenfunctions of Lx and Ly. Now what is the physical implication of this? Suppose I make a measurement of the z component of the angular momentum. I have a particle in some arbitrary state. I make a measurement of the z component of the angular momentum. Once I make a measurement of the z component of the angular momentum, it will go into one of the eigenfunctions of the Lz. Now these will not be eigenfunctions of Lx and Ly. So once, if I know the Lz, the z component of angular momentum precisely, then I will not have precise information about Lx and Ly, because these are not eigenfunctions of Lx and Ly. So if I make a measurement of Lx now, I cannot in general predict what value I should get precisely. Okay, so these will be superpositions of eigenfunctions of Lx and Ly, and I can only give probabilities for different values of Lx and of Lx, let us say, if I make a measurement of Lx after I have made a measurement of Lz. So this gives us some uncertainty relation between the values of Lx and Ly, Ly Lz, or Lz Ly. Okay, because I cannot precisely fix the values of all three of them, because I cannot have simultaneous eigenfunctions of all three of them. Okay, so we are brought back to the uncertainty relations once more. We have seen that the wave nature gives us forces us to have some uncertainty between the position and momentum. Here again we find that there is some uncertainty between the different components of the angular momentum. The uncertainty relation is basically a consequence of the commutation relation. If some operators don't commute, then there will be some uncertainty relation between the expectation values of these quantities. Okay, and the exact relation we shall derive later on in the course. But you should keep in mind that there are uncertainty relations between the expectation values of L square, Lx square, Ly square, and Lz square. So for today we shall stop here. In the next class we shall work out the eigenfunctions for the set of operators Lz and L squared. So are there any questions you want to ask? Have you encountered the Poisson bracket in classical mechanics? Oh, you have encountered it. So you know the equation of motion also, right? What is the Poisson bracket equation of motion?